Okay, and let me share my screen. All right. I hope you can see it, right? The screen.
Yes, sir.
Yeah. Yeah. Anyone wants to say something before I begin? Okay. So in the last class, as you have seen in the last class, where we started off with linear classification problems. So our goal is to have a set of data having the attributes, let's say x1 and x2. We have some data as plus and some data as minus. And what we are doing is we are trying to fit a line which will separate these two data. And hence, we are only bothered. So our learning algorithm is trying to make out a particular line, that is from I equal to 0 to d number of attributes. And obviously, since we have w0 and x0 equal to 1, that is our assumption here. To make this thing look like a matrix format, we did it sum from I0 to d, and which says that this is our line equation. And while getting a new training data, what I try to see the sign of this upon getting a new x, and try to classify whether it's a plus 1 or whether it's a minus 1 class. That means whether it belongs here or it belongs here. That's how we did a linear classification in yesterday's. We will see more on this, particularly perceptron learning algorithm in today's class. But the first algorithm that we gone from linear classification and moved into linear regression, which we find in our day-to-day use, because many a times we need to fit and need to find a value for that. So the only difference between classification and regression is that at end you need a classified class, whether it is plus 1 or minus 1 in classification. However, at end in regression you need a value. So you can easily see I can extend this in linear regression by saying that I will just report this as a value, whatever be the new x provided. I will not go for the sign. And in that case, an interesting term that we coined up is the square error term, which we try to minimize. And doing the minimization with respect to the weights that it will get minimized, we try to figure out what is the average error that we are getting. So error for a term means what will be the ith value that is being given in the training example when you feed xi yi, each training example, and what is actually that value will be with respect to your line that you have predicted as your regression line. That is our error. And obviously I equal to 0 to the I equal to 1 to the number of training examples. And when you try to minimize this one, we figured out that we say that it's a partial derivative of all this. And suddenly we figure out when we try to minimize it 0, we have a one-step process of finding the weight, which is nothing but x transpose x inverse into x transpose y, where as you can, if you understand, x is our each of the training example attribute values transposed are the rows. So I have all these n, capital N training examples, and y are the output values for each of the training examples. It's a one n row and one column vector. So we have y1, y2 up to y capital N. And then this is a one shot thing. So if we do that in one shot, we could learn all the W's, and that is where we fit the linear regression line after seeing each of the training examples. So we call it as a one step or a batch kind of a learning where we one time do it. And we have also seen that a linear regression effectively tries to minimize the error boundary. So what actually happens in the visualization? So suppose I have weights in this direction and I have error in this direction. So there are different weights value. So W0 and W1 value, this is in the bottom plane. Different weights value will give rise to different error. And we have seen that in case of squared error minimization, it usually is a cup-like shape due to the squared error formulation. So I forgot here is square. So now this is kind of a cup-like shape that we get. And what we do with this learning, we are trying to find out the weight vectors which is in this position. That is, it minimizes the cup-like shape error. It minimizes the cup-like shape error and find the best possible weight combination through this. That's what our learning was. So, however, as we have seen that in case of linear regression, so effectively when you go for linear regression, what you do, suppose you have an x and you have an y, and suppose your data are distributed like this. Now in linear regression, obviously, in our case, I was trying to fit a linear line for that value, and usually your data looking into it doesn't follow that way, though we are purposefully fitting it in a line in such a way that we could reduce the total error that could be made by fitting this line. It's an optimization problem which we are trying to solve by reducing the error. It's an optimization problem we frame by error minimizing. But however, in practice, this is not the case. We would be rather happy instead of this if we could frame out such kind of a regression line. Or even we would be happy if we could at least have an approximate some kind of a curvy like line. So this is what there are interesting ramifications or variants, I would say. It's a ramification of linear regression that I will see today. And on the other case, in the linear classification, it is very good technique to classify which are linearly separable points. However, in practice, you often see that your points may not be linearly separable. Let's say there are some points like this, there are some points like this. So it's no way linearly separable. So such cases where there is not linearly separable instances are found. So our second thing that in today's lecture we will see that how we apply linear classification in those case of examples where the data is not directly visible as linearly separable one. So by this we will start, and we will see that how this linear classification and regression thought process leads us to something called logistic regression, which is basically merging the probabilistic aspect of learning, that learning what is the probability of y given x using maximum likelihood, and the generalized learning where we are trying to learn a function. All those two C's will converge together when we declare something as a logistic regression. We will see these three things in today's lecture. So to start off with, let us first start off with the variant of linear classification. So when I say variant of linear classification, I would like to mean that if my data is not separable in a linear sense. Suppose I have x1 and x2. Suppose my data are like this, like this. So therefore, you can see your input matrix would be 1 is the mandatory x0 and your attributes x1 and x2. However, no line. Well, wait a minute, maybe the distance from the center to each of these points, these are nearer and these are farther. So why not I give a transformation to this data by having this attributes which captures the distances instead of just the raw data as given. So if you go for the distances, you will feel that then the data that I was given looks like this, which is obviously I can find a linear separable line. So for handling non-linearity, we have an engineering technique now. What we do, we are given X as an attribute. We transfer into a different attribute set following a transformation of those data over that X and found out this. Now, since this is linearly separable, then what we do, taking this Z, we try to find out this kind of W transpose. I wrote it tilde because it's in the Z space. And then finally convert this W tilde to my original W space of the weights. And eventually what we find is that instead of, due to this shift in the domain and then coming back of the weight, instead of a linear separability in the x1 square and x2 square space, I got this kind of a thing in the original space. Intuition wise clear what I was trying to do? Is the intuition?
Yes, sir.
Yes. So if that is the case, now some small things that we need to consider here is that I am trying to transfer my attribute space into a different domain. So there could be multiple options. One option is that most generic option that I will compose every possible combinations into that quadratic domain as my attribute set. Because this is the most generic case. The most generic set of attributes that I could formulate while doing my transformation. So this will be more apt, but the problem is that the dimensionality increases because dimensionality is now with respect to the number of attributes that I'm making. And hence, if the dimensionality increases, in theory later we will see the generalizing or the goodness of your learning usually is more bad. Because if the dimensionality increases, the number of attributes you may get will increase. And if the number of hypotheses, the number of hypotheses increases, if the number of hypotheses increases, if you remember the learnable feasibility concept, it is a probability of learning is restricted by 2m. Hövding inequality is multiplied by m. M is the number of hypotheses. Since the space will increase, the generalization will be difficult. And computationally also, it will be much more difficult to go through this space and to find out each of the weight. Rather than finding 2 weights, 3 weights, here you need to find out 6 weights. So that is computationally heavy also. You can also think of the thought by looking into this. This gives us a reasonable approach because the data distribution looks like that. You can have a third idea that, well, as per the data I am looking, if I look very carefully, maybe these two attributes will do because it's the distance from the center and a constant to fit the line that you are only doing it. So effectively, I only need not the two attribute space, I need a single line as my attribute space where all the 0 points will be nearer and all the plus points will be farther in this line. And I just need a divider. I just need a W0 divider for that. However, if you look even more closely into this, you can find I can do it within one attributes also. Because if it is greater than 0 plus, if it is less than 0, it is 0. If you see this, this line formulation, it will be like that. But see, why we do not prefer this or this or this is the fact that this is the most generic and by
Sir, I didn't understand the last one.
the last one is if you have only one attribute, which is this. Okay. If a new point comes, you will just say if it is greater than 0, you class it as plus. If it is less than 0, you class it as 0. We can do that now in one attribute.
Okay.
Check this attribute. If the circle line is itself like this, you can do it in one attribute.
Yes.
So that's what, but the point is, we always need to follow this generic transformation rather than this, because otherwise, see why you thought about this, looking at the data distribution. Why you thought about this, more looking at the data distribution. Why you thought about this, more and more and more looking into the data distribution. So the way you are thinking in each of these lines is that you are learning from data which machine needs to do. Are you getting my point? What I'm trying to pitch in here. See, this is the best. But this is what? You know the data, you learned it, you gave a circle. So you are learning it, not the machine. However, for machine to learn, if you give this one, machine will learn the weight. Even if this one I will admit, because at least you give some flexibility to the machine. This one, are you learning it about the data distribution? So this is a caution while you do the transformation in nonlinearity. Many a times people try to do it themselves rather than by the machine. And we call this kind of misinterpretation of the data by themselves is called data snooping. And this is we need to avoid, because if you see the data and frame a model, you are not seeing the test data. So the generalization that can be done is from your thought process, not the actual process that is followed for generalize, regularize, all these things. So when people do think this way, usually in the test data, they perform bad. So therefore, in the transformation domain, you try to keep the whole attribute space as much as you can. If the dimensionality is more due to computational efficiency, you can reduce it to certain, but not freeze it somewhere. Okay, that's the lesson. But the more important lesson is this one that I told, that for a nonlinear space, if you could find out a suitable linear interpretable space of attributes where it is linearly separable, push it to there, take the WTs or the weights in that domain, convert that domain weights into the present domain that you are trying to classify. You will see the classifier you can already get it. Okay, this is the variant of linear classification.
Sir, 1 comma x1, sir, 1 comma x1 square plus x2 square and x1 square plus x2 square minus 0.6. They are similar. Just the radius is different.
But in machine learning, one attribute less is less computationally it is more computationally efficient than this. See, in machine learning, they will try to find here only W0. They were trying to find here W0 and W1. They are trying to find here W0, W1, and W2. Computationally, it is getting bad, na?
Okay.
Now, the second aspect that I told, that it's a variant of linear regression. Again, I will start with giving you the intuition. If you understand the intuition, then the mathematical jugglery will be simple. I think you know the solution. Just I need to trigger you to think in that way. Here you see, instead of fitting a linear line in the linear regression, what we did, where we missed out is that we do not, we see every point together and fit it. That's why a linear line we came up with, which minimizes the error. Rather, if we could look into a local space, then we could have a better understanding about the curve. I hope you agree what I am saying.
Yes, sir.
So therefore, for a new point that is given to you, what you try to see, that suppose this new point y will be this one, which is not present in your training set. Only the cross points are in the training set. So suppose a new point x is given to you. You will see a local space of the new point within, let's say, a delta limit. You remember the KNN principle? That principle we will just apply here and try to have a linear curve fitting there. Try to have a linear regression curve fitting there and just seek the value, what it is. So effectively, what you try to do here is that you try to piecewise fit certain positions within delta intervals. You piecewise fit this, isn't it? Within a boundary. If you are here, you piecewise try to fit here. If you are here, you are trying to piecewise fit here. So therefore, it gives rise to an interesting, just a small ramifications to it. Here also, you try to fit by getting your W values such that it minimizes the error. But earlier, your error was with respect to all training examples that you are trying to fit in, which was your WTXI minus WI square. And you are trying to minimize that. I'm just removing 1 by n. I mean, it doesn't matter, that constant term. Here, you try to minimize this within a boundary of delta. Wherever your point is, you try to minimize this within a boundary of delta. That constraint, I will give it by alpha I, mentioning that my alpha I is equal to exponential, that is e to the power minus your given point, this square by 2 tau square. You can see where this expression comes from. Let us try to understand why we did it. First, let us try to understand what happens if if not the alpha I. Suppose you are given that this expression, suppose your point xi and the point that you are trying to estimate is very far, that is, this is very large. If xi and x is very large, then what will happen to the minus x, this formula? If it is very large, then your alpha y will be tends to 0. So when alpha I will be tends to 0, so very far away point xi from my current point that I am trying to find out the value of will not be considered. Are you getting it due to this formula? If your xi minus x is small, then your alpha I will be close to 1.
Sir, are we fitting a bell-shaped curve near that region, which decides how much importance we need to give to how far point?
Yeah, your second point is correct. Bell-shaped curve I am coming next, because this one will resemble that e to the power this thing.
Yes,
We
sir.
are trying to fit in a piecewise linear thing from the point of our interest. Suppose I want to get this value, I piecewisely try to find something. I want to get this value here, which is not there in the training data. I piecewise try to find it. So why this? Because this has as your friend said, it has a bell shape. It's like Gaussian, but the only 1 by 2 pi root tau is missing. It's a bell shape where this is tau, and you are trying to point a point. Your mean is x, your x point. Now see, the farther point contributes less. The farther points, as you can see here. The nearer points contributes more. With respect to tau, I can adjust this boundary. How far I would like to visualize. If I have much more tau in my bell shape, then many points I would like to see to decide it. Get the idea?
Yes, sir.
So
Yeah.
so this alpha into the whole expression something squared. So this is the error.
Yes,
But
obviously. Earlier the error was without alpha I, because we are considering every point into it. Sum of all.
but don't
Now my
but
alpha I will contribute further point as 0 and nearer point as 1. So only the nearer points gets contributed to the error.
but that is wrong. No, sir. So the farther point they will also contribute.
They will contribute. I mean, it tends to 0. It's not 0. They will contribute. And if you want further point to contribute, you relax on your tau na. It's on your hand. You relax on your tau.
But xi minus x is not the farther point. It's at the same level.
No, for all i's I am saying. For all i's where your point and xi has a distance more, then that will contribute less. For all i's where your point and the xi has distance small, will contribute more due to the bell-shaped nature of the contribution.
Okay, sir. Okay.
So what is x here?
X here, the point of your interest. That is your new point that you want to know the value of. Crosses are the training data. So after the training, what we do? We give a random point and I ask you for the value of it. That is the random point is X. You do not know from the training data that point. You need to fit in and find out the value. So it's just a piecewise linear fitting with the width of the piece from coming from this bell shape. That's what I would say. And the concept that I just explained is called as locally weighted regression, because it weights the points locally, further gets the lesser weight, nearer get the more weight, and therefore if your tau is very large, you will just get a linear line of kind of a thing. If your tau is very small, then you get very small pieces of like this kind of a fit. You are getting it, right?
Yes, sir.
Yes, sir.
Just try to
Your
ponder on
tau
that.
is standard deviation, right?
Yes, tau is standard deviation, obviously, but this is not a Gaussian. So we do not say it as a standard deviation anymore. It's a bell-shaped curve where the middle of the mean is this one and tau is the difference between this. See, standard deviation and all these terms are due to normal distributions and Gaussian relationship. In the bell curve, we call it just deviations. Mean
Deviation.
deviations. Mean. This is the mean and the mean deviations. Deviations with
Okay.
respect to mean.
Sir, basically this bell curve is a weighting function, means how much weight we
Yes.
want to give to the points which are at a
Yeah.
distance from X.
Exactly.
Why are
Bell
we
curve
specifically
is a
selecting bell curve only?
no. You can select different curves, but it results it. As I said, machine learning is more of common sense and applying to that. If it results like spam filtering, I mean,
Yes, sir.
why conditional independence matter? It results well. I am not saying it is the
So,
optimal the algorithm.
so normally bell or Gaussian curve is used when we have randomness in our data. But if we are talking about linear regression or the curve we are seeing right now, it has a certain specific pattern, like we are trying to fit the straight line in. So,
No, straight line will give you bad estimations rather than if you have this kind
no,
of a
in that
function.
region, in the region surrounding X, we are trying
Yeah,
to
the
fit a
regions
straight
the
line.
surrounding x, I am fitting a straight line only. I am fitting a straight line
Uh,
only in the region surrounding x.
yes, so that's what I'm saying. By looking at the region surrounding X, we can say that the points are not arranged randomly. But while
No, but
deciding the weighting function, we are using a bell curve, which is generally used for randomness in our data.
correct. This is also, I mean, that's what point I will try to make in. This is also used for noisy data as well. So usually what will happen, see, your car will look like a fixed safe. So suddenly there will be a noise and then again it looks like a fixed safe. So therefore it is like this, but suddenly due to this noise, how can you cater to this noise? So that's why people assume that within this boundary, 1 point deviation doesn't matter too much in this linear fitting. It would be like this in the top position.
Okay, sir.
Okay, so just take an example and try to do this one. You will figure out, and take a noise also. Take some points here, 1 point here, and see that it will. What will happen in the noise? You see the linear. It will minimize the error. So your line instead of here will be here. So instead of this, you are getting this one a little bit bad, but not too bad because of your contributions like this.
Yes, sir.
Okay. Now, as
Is
I
that the
mentioned
case? Is
that,
that the reason?
excuse me.
Hello, sir. I'm
Yeah.
asking the reason behind using this bell curve can be like the curve what we are observing. We can divide it in different bell-shaped curve, right? Like the
No. That
above
is not
one,
the. No.
we are referring it as locally.
No. It doesn't matter about the distribution of this data. See, this is how you consider your neighbors. Your If your neighbors doesn't look like this shape, also I can consider it in this way. This is about my contributions of my neighbor. It looks like kind of a bell. I am assuming that the contribution is kind of a bell. If you assume the contribution is kind of is constant, then you do this. No point, no issue.
Okay, sir.
Okay, it depends on the application. Okay, so now I would also like to point that all these points out to our the familiar problem that we started off with. We want to know the unknown f from the x and y pairs, which loosely translate into the problem of finding the probability of the value of y given the values of x. And we say that these two are interchanged problems. We can visualize. So since many of the cases occurs where we need this, for example, if I want to predict heart attacks. So predicting heart attacks is usually that it's a probability or a percentage. So it's from 0 to 1 it will get. And it's a real value between 0 to 1. So it's a typical linear regression with a boundary. And you cannot say that something is too specific. There may be something too specific, one boundary, and something may be too specific which has zero boundaries. And in between that, it may not be just like in threshold function, we are doing +1 and -1. Let's say it depends on the age, blood cholesterol, sugar, and all that. So it may not be like this, that within this age and blood cholesterol, drastically you will be one probability and otherwise you will be zero. It should be something smoother than this. So many a problem it occurs that there are an uncertain zone in between than two certain zones. Or in a way, we call this kind of functions as sigmoid functions. The name comes from the fact that it looks like an S, which is the first letter of sigmoid. Or sometimes also we call this as the function we call as a soft threshold instead of a hard threshold classification that we do as 0 or 1. I mean, it is in this class or this class. So as you can see, such examples can be used. So we call such kind of a function, usually this due to the shape of this function, there could be multiple ways of writing such kind of a function. One of the ways we usually do is this kind of function exhibits such behaviors, which can also be written as, if you divide both sides as by e to the power s, you'll get this. This exhibits such kind of a behavior. Similarly, you can also see a function that hyperbolic tan of x also behaves in this way. So our job is now that getting the summation value of s, which is from 0 to d number of attributes wy xi, or in short we call it this. We want to pass it to a smoother function and then get our hypothesis. So therefore, we are predicting our hypothesis s as nothing but if the smoother function is theta of the sum, it is theta of s. Okay, so this particular type of regression problems, or I would say the probabilistic view of interpretation of regression problem, we call as logistic regression. The name comes from the fact that it has a logic certainty after beyond a point. It is regression because it predicts a value, and there are points also you can see in between where it behaves almost linearly somewhere in between. So it's a linear separator. It has a specific logic 0 and 1 to classify. So all three comes together, and later we will see it's also easily differentiable due to this continuous nature rather than a jerk 0 to 1. That will come in the later lectures. But due to
So
this
by
point,
taking theta of s, so
yeah,
by taking theta of s, we are just making it smooth, right?
yes, we are just making it smooth and making it between 0 to 1, a probabilistic value. Otherwise, it was a sum.
Okay.
Okay. So therefore, now you will see that in this logistic regression, what we want to do, the probabilistic interpretation of it is that you are given with the data x1, y1 up to xn, yn as your training examples. Now you try to probabilistically look for, you're trying to find a hypothesis that best fits the likelihood of the data. Remember maximum likelihood estimation, that I want to predict some theta that maximizes the probability how my data will behave. Yes or no? Remember this?
Yes, sir.
So
Yes, sir.
therefore,
Yes, sir.
what you want to do, probability of y given x is basically, I want to find a theta which is this form. But you see, probability of y given x, my y is plus, I mean, my y, I would say that rather, let me pitch in this way. Let me revert back what I was saying. I want to find a hypothesis in such a way that I want to find this when my y is equal to +1. Since it's a probability, therefore probability of this is not occurring will be my hypothesis this when y equal to -1. I just want to figure out such, as it has a probabilistic interpretation. Now look at the theta s function. What does theta minus s tells us? What does theta minus s tells us? It will be 1 by 1 plus e to the power s, which is nothing but 1 minus of theta s. Can you see this?
Yes, sir.
Yes,
So
sir.
therefore you see my hx, as I have told, my hx will smoothly pass through a logistic function. So my hx is nothing but theta s. So this is nothing but theta minus s. Ultimately, if this x is passes through the sum, and then I pass my sum to a smoother function, sigmoid function. So what I want in this type of probability of y given x is that theta s if y equal to +1 and theta minus sum if y equal to -1, which is loosely I can tell it that I need theta of y into this for all training example points. So when I go for all training example points, this probability should maximize my likelihood. Consider the coin flipping examples. I am trying to maximize my theta in the coin flip, where there is coin flipping done, head is theta, tail is 1 minus theta, and so on. I am going on. So to maximize, I need to maximize the probability of training points from all examples, which is basically I am trying to maximize through my maximum likelihood estimation.
Sir, I didn't get the last equation that you wrote
See,
in
you
place
are
of
trying to
S.
this one. Oh, the last one means here. How do I wrote this one or this one?
So second last,
This one.
in place of S. So why?
Oh, in place of s, s is the sum. So s is nothing but here your s is nothing but
Okay.
s. When s is the sum, either s equal to this +1 or if it is -1 this, so I can just multiply y because my y is dictating that. So now this is my probability that should maximize my data, because data is drawn from some distribution, and as we have seen in my probabilistic interpretation that I should find some theta that maximizes my data, and my theta is my outcome. That outcome maximizes or resembles best possible way with my data. That's what my goal is. Agreed?
So according to Y, we will consider the S, right? Maybe it's minus S or okay.
No. Not according to y. S will always
No,
pass
sir.
through theta.
Actually, I'm talking about the reason why we are taking the Y. So if Y is +1, then we are taking S, and if Y is
So
-1,
y
then
is
we are
here
taking
plus
minus.
one. Y is +1. I am saying it's surely that he will get a heart attack. Y is -1. We are unsure that he will get a heart attack. So obviously, when I can give a hypothesis which surely predicts a heart attack, so 1 minus of that hypothesis will surely predict it's not a heart attack.
Yes, sir. Yes, sir. Got it.
That's just a mathematical jugglery, nothing else. Intuition wise, you got the intuition if you understand this only. The rest I will just follow it as it's a probabilistic interpretation.
So, sir, the question is why we are using theta inside, like why inside theta, xi?
Because the unit is passing the sum in the theta. Na? See, you have what you do, you have this x1, x2, all these attributes xd. You pass it to a sum unit, you pass it to a smooth unit, and then you get it. Passing to a sum till the sum unit, you get a logistic regression. Unless you pass it to a smooth unit, you do not get a probabilistic thing which resembles 0 to 1, this smooth value, and which is obviously this kind of application dependent, because I need a smoother probability value variations from 0 to 1 depending on my attributes. Instead of this type of function, you can choose a hyperbolic function as well to make it smooth. So this is a weapon. This is a weapon. As I am saying, I will show the applications of logistic regression in the next lecture. These are the weapons. Classification, regressions, these are the weapons. Gradually, it will be used to build up my multi-layer neural network. So all the weapons I am seeing, one weapon is just use the sum in regression. One weapon to classify it drastically in the threshold, jump from 0 to 1. Another weapon is smoothly do it, which has a probabilistic interpretation that I am trying to pitch in. Get it? Okay, let me proceed. So then what we are trying to do, we are trying to maximize which means is same as minimizing minus of this thing. Just I put a minus here. Why I'm coming here, it will be, if I do the maths, it will be just easy to know. Which means it is same as minimizing this. Which means it is also same as minimizing Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
So what is this one? That means I want to minimize putting log inside it. Theta of this one, I know theta of S is nothing but so if I put log inside it, so this will be this means I want to minimize. So let us take the minus sign inside every sum. Now see, I want to minimize this as my in sample error. Earlier in, so this is my logistic regression. Earlier in my linear regression, I tried to did the same thing while I was minimizing 1 by n summation, this is summation over I, this. And due to such nature of the error, so what I will do is that this was earlier my error. I said as some squared error. Here also see there is same thing. This is your error with respect to the hypothesis that you built in, and your yi, actual yi that you get in. This is the error. Earlier, this was the sum squared error that you try to minimize. The same thing we will do as in linear regression, but due to the sum nature and the log nature here, in the first case here, we could have a one-step solution when we try to minimize this optimization problem. You remember the solution? The solution was this. Isn't it?
Yes,
One-step
sir.
solution. Here, due to this nature, you do not have a one-step solution. Here, what I do when we do not have one-step solution, but we know programming, we go on doing iterative solution to get the W's. So what I mean by iterative solution here is the fact that, now coming back to this, that I will look into each of the training examples one by one. Okay. And what I will do is I will try to predict the weight as the earlier weight minus some learning factor or the step size, we will say, and I will move into that with a unit vector gradient. Let me explain what I am trying to do. Suppose this was my error surface. I have a rate in which I will uniquely move towards the gradient to find my minimum. That unit is nothing but how I would differentiate with partially differentiate this with respect to each W. This is a vector. If I divided it with its by norm, I will get the unit vector. This gives you direction. To illustrate more, suppose you close your eyes in your room and your room, the surface of your room is not plane. Suppose in one axis it is a little bit downer, the other axis is a little bit upper and like that. And you want to find out something in that room. So you close your eyes. Now you have some informations about the gradients of different side, which side moves where. You calculate the direction, that in which direction if I go for one step, then I can reach towards my local goal of finding that particular key, and you move one step at a time. So your step size is this and your direction is this. Earlier in linear regression, instead of one step, if you have done it one by one with each training example, you will gradually do the same thing. But we did it in a batch learning way. Here, we will do a gradient descent iteratively. Got this concept?
Yes, sir.
Everyone, any questions
Yes,
here? What I was saying?
So
Dog
that
will have
last
bell shape curve.
So,
direction.
One by one. In the last direction, please complete that question.
So the direction thing I'm
is
not
it
understanding.
Okay. Anyone else? I will explain. Okay. Let me explain the direction. This thing as a whole. When we are trying to minimize this, what we are doing is that we
so
are trying.
intuition wise it is clever.
Yeah, if it is intuition wise clear, the mathematics easily we will do, and we will gradually do in tomorrow's and next classes and all. So this delta, this reverse delta thing that I am mentioning here, reverse delta E in W, is taking the partial derivative with respect to every Wi. So it is just taking your delta in with respect to W0, your delta E in with respect to W1, and so on. What does this mean? Each of these terms here means that with respect to that particular weight, if I change that weight, how good or bad I am doing. And it's a cluster of them because it's in d-dimensional space. So that means if you consider the two-dimensional place in your room, if you close your eyes, you know in the length side, suppose in the east side, if I move, okay, I will go down. In the west side, if I move, okay, I will go this much down. So, okay, my movement will be something resultant in between it, where I could go steeply down. But you cannot go beyond one step size because that is your step size. Your step size will be more, my step size will be less, someone's step size will be bigger, Usain Bolt's step size will be much more. So that is the intuition. What we will do, we will take one by one example. We will try to partially differentiate with respect to each of the weights with respect to only that example. Suppose turning example 1, then turning example 2, and individually each of the weight we will just update. So taking training example 1 and updating a weight means that you are reducing the error with respect to that training example. Again with respect to another training example, again with respect to another training example. But you are reducing weight resultant. That means every possible weight combinations you are trying to figure out which is the best resultant to go. But you can go only with you are restricted to move with respect to your foot size. So the direction is given by this, the derivative and its norm value, it's the unit vector, and you are moving to that step size. Now the question is how will the step size will be more or less? So if you typically see that if this is my error surface, if my step size is very small, then I will just go very small step and it will be very long time before I converge here and do not find any better gradient. If my step size is very large, then I may go haywire, I may oscillate. If my step size, so actually what people do initially in the initial position, how do you tune old radio for FM channel? Initially you tune faster. When you get the signaling just coming in, you tune slowly. So initially you make your step size more, then you gradually reduce it and fine tune it to reach here. So that is if eta is small, if eta is big, and eta is adaptive. This is how in the error surface we move and converge. Okay. So now if you can see that if I take a derivative of the whole thing, you will see that what does, to finish off the mathematical equation, what does E in W means? It's basically a derivative of the thing. So if you take a derivative, you will get yn xn. So see, I need to take a derivative of this with respect to each of the ith point. When you take a derivative of this particular thing, so this will come 1 by the whole thing and the derivative of minus of this thing, right? Minus of this. So minus of this will only occur if you take partial derivative, only del I term with wi will keep. So when you take partial derivative, so it will be, so as I said, del ei in w is nothing but taking partial derivative of E in with respect to d0, del E in with respect to W1, and so on up to del E in with respect to WD. Now, what is this one? So if I say if I take partial derivative with respect to W0, then instead of doing this one, first let us do the one by one. So then what will come is that the log thing will be 1 by n is earlier, the log thing will be 1 plus e to the power minus that yi w to the power t xi. There was a sum that will do for every cases. Now here this term will be, we take a derivative with respect to w0. So when we take a derivative with respect to w0, what will happen to this term? Yi w t xi. You will only have yi0 xi0. Yes or no?
Yes, sir.
And a minus here. Right? So in this way, you keep on doing for every term and take this delta in vector. That's what this will result. See, I am not doing the calculations, but going for the intuitions, because any book you open, the calculations will be given. Only the intuitions is less given. That's why my feel. Anywhere you open it, you will get this calculation. It's just differentiating partially with respect to every weight and making it as a total vector. That's it. So when so our major term that we are trying to minimize here looks like this. As I have seen, e to the power minus y I w t x I for all I. We call this, instead of error, we call this as a cross entropy error. In the book, you will find this as a cross entropy error. And this is what we call as stochastic gradient descent. The algorithm that we mentioned, that stepwise we will try to modify the weights with respect to each time step. We move on with respect to every training example we scan in until we reach, I mean, when we stop, how far in the t we will move on, how many t's, that depends when your slope is not increasing beyond the threshold. You iteratively go on with the step size movement with respect to this unit vector of the error margin. Okay, so this is how we do it in three cases. So as you can understand, one is you have only the sum unit as your hypothesis. This is linear regression, linear classification. The other one, so in the sum unit in the hypothesis, you have at the end, you just have a drastic 1 or 0 to mention +1 or -1. The other one is the regression, where you have just the sum. This is linear regression. And in the logistic regression, after the sum unit, you have a smoothen curve to make it within probability 1 to 0, this factor. This is your logistic regression. And what we studied is that in order to make this linear line here, what we did, we just had a weight adjustment, which is a perceptron learning algorithm. We will see how to adjust the weight. We will see in both cases. In here, since it's a drastic function up and down, we could also see gradient descent as well as stochastic version of it. In linear regression, since it's a one formula and it's a summation error that we are trying to optimize, we could directly look linear regression as a one-step solution. Logistic regression, however, the function of the error or cross entropy error that we are trying to minimize is differentiable in nature, that is fortunately for us, and also cannot be one step solved. So we gradually take each of the training examples and try to figure out where we should move in order to get a minimum error solution. That minimum could be, unfortunately, a local minimum, but you will reach some minimum there. Okay, with that, let me stop today's lecture. If you have questions, I can answer.
So we will take some initial value of W, right?
Yes. Usually some random initial values of W's are taken.
Okay.
And it's a very good question because there are several research where to start.
So the term stochastic
According
and
to it
stochastic descent relates to randomness, right?
No. Here the stochastic terms is only that the full set you are doing it together or you are doing it stepwise. The stochastic, as in opposed to statistical meaning, it's not like that randomness. So you are right in pitching out the randomness, because what will happen, see, usually the error surface looks like haywire, like this. Now, as I said, I choose a training example 1 followed by training example 2. So the order in which I choose the training example, I may start with here, gradient descent here. If in some other order I have chosen, I may have started here and descended here. So therefore, it's randomized in terms of the choice of your training example, and that randomization is good unless you may also choose some here and reach here. So usually people found such kind of thing, as you said, brings a randomization in finding the minima, because I am now free to choose the training examples in arbitrary order, and that ordering gives me the starting position. So depending on the ordering, my first change of the weights or my initialization of the weights will come in with this and the ordering. So that's why people use the stochastic name to it, but I would rather say it doesn't resemble with the stochasticness. The randomization resembles with the initialization of W mostly, where you will start your W's to start. The randomizations in the training example is less utilized in searching this local minima, but people call it stochastic gradient descent just as a name to pitch in for this randomization. But however, it's just not a one-step batch thing. It's a one-by-one thing.
Often
Hello,
we
sir. I
just
have a question.
shuffle the examples,
Oh,
and
Mhm.
so in that scenario we call it stochastic gradient descent, because we are shuffling the examples.
No, 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 no. That is not the case. That is not the case. See, shuffling the examples is a different thing. That's what I want to pitch in. Initializing W in random is the most important, because your error, this gradient will is dependent on the values of W's. So the starting point is one particular initialization of W. You can start here with a different initialization of W vectors. If in the three-dimensional space, if you look at the curve, this is your W, 0 and W1. So if you start here, you will descend this side. If you start here, you will descend this side. You can see the choice of W0 and W1 matters in the position where you are starting with. That can be randomly chosen. The occurrence of the training example randomness will only give you better solutions in terms of the number of steps to converge. That's it. There the randomness will not come by shuffling the training examples.
Okay, sir, clear.
Somebody
hello.
just want to yes,
I have a
please.
question. Sir, in stochastic gradient descent, we always ends up to local optimum solution.
Yes,
But is
local.
there any way that we could end up to global optimum solution?
Unfortunately, no, because the problem is NP hard in computational sense.
Okay.
It's an NP hard problem.
So it actually depends on our luck, means
No,
from
not
which
lucky.
point we should
I mean,
start.
it depends on the luck, obviously, and no, you do cross validation multiple times.
Okay.
Randomizations of the weights, cross validation, shuffling your training examples to see the convergence and all.
Okay, sir. Thank you.
So is that the case? We will do it multiple times and we'll do the optimal one. Like taking the
Yeah,
W
usually we do that. We do cross
randomly again
validation
and again.
usually. Yeah, usually we do that. You usually randomize 6, 7, 10 times. We do cross validations with a multiple training and test classification of the data, and we run it multiple times. Where we get best accuracy, we keep that W to start with and train our model. And finally, that model goes in. The parameters goes in. So it doesn't. The initial weight goes in, but only the parameters W0 to WD goes in as part of your model.
Okay, sir.
Okay, so let me stop the recording.